So in this video, we're going to explain one of the most common errors that are found in introductory textbooks that talk about mid-ocean ridges. So for mid-ocean ridges, we have a process that's called passive mantle upwelling, and we'll compare that to active mantle upwelling in a moment. So what happens in a mid-ocean ridge is that we have a piece of lithosphere, and there is some area where it's going to break. And where it does, let's start out with some stretching where we start pulling this piece apart. This is supposed to be the upper surface. This is the lower surface. So we're taking this break and as we stretch this material, it becomes a little bit thinner here. And then eventually we get to the point where we have an active break. And that active break we think looks something like this. So this is the ocean floor there. This is the mantle lithosphere that gets thicker as we move further away from the mid-ocean ridge. In this area here, that's the mid-ocean ridge, and we'll just abbreviate that as MOR. So what's happening down here in the mantle? Well, in the mantle, we have hot material. So in our initial case of lithosphere, we've got hot material sitting down here below the lithosphere. As it stretches, that hot material is able to rise a little bit to somewhat shallower depths. And then when we have a full break, that hot material is able to rise to much, much shallower depths. But this process of that warm material invading this area underneath the mid-ocean ridge is completely a passive process. We mean passive because even though this material is hot here in our first case where we have unbroken lithosphere, the mantle really isn't doing anything. It's just sitting there at some higher temperature relative to the lithosphere, but it's not punching its way through. It's passive upwelling in the sense that it's only when we break the lithosphere apart that the mantle is able to move its way into this gap. So what that means is that there are no jets of material that are forming mid-ocean ridges. So what's the most common error when we look at many introductory textbooks? When they show a mid-ocean ridge like this, let's say here's another mid-ocean ridge with the lithosphere moving apart and getting thicker as we move away, they'll show big convection currents that are rising upwards beneath that mid-ocean ridge. That is almost always wrong. Now I say almost always because there are some places where you do have hot jets of material rising underneath a mid-ocean ridge. We think Iceland and the Galapagos Islands are places where you do have a mid-ocean ridge where there is indeed a hot jet of material that are rising upward, that these are parts of the upwelling limbs of convection cells. But the convection that drives plate tectonics on Earth is being driven by heat at the core mantle boundary. So the core mantle boundary we'll abbreviate as CMB. It's very hot. It's pushing heat. It's pushing both heat and material to rise upward towards the surface, but it doesn't happen in a mid-ocean ridge. It drives volcanism at places like Hawaii that is far away from a plate boundary. The plate thinning, if we draw the lithosphere here, this is not to scale for sure, but if the lithosphere could be very thick at Hawaii, and it could be very thin over here at a mid-ocean ridge. And then this would maybe continue over here somewhere. Don't worry about that part of the diagram. So a mid-ocean ridge has very shallow source for its volcanic material. That's a place of passive upwelling. So the mantle material rises up passively, and then this mantle plume is a site of active upwelling. So this upwelling is active in the sense that there is this excess heat relative to the ambient mantle. Heat that's being dumped will represent heat by Q. Heat that's being dumped from the core mantle boundary into the mantle and is causing this buoyant jet of material to rise upward and drive melting regardless of what's going on here at the surface. For a continental rift or a mid-ocean ridge, we have this passive shallow source of upwelling. The upwelling is only to fill in that gap created by pulling apart the lithosphere in that location. So that's what we mean by passive and active upwelling. Both of these are examples of so-called adiabatic rise. When we talk about an adiabatic rise of the mantle or adiabatic melting, What we mean is that whether it's passive or active, this material rises up fast enough that we don't have to worry about heat being transferred by conduction. So conduction is out of the picture, and it's only the heat flow that is relative to convection that is important for understanding how much heat will be transferred either to the shallow part of the mantle here or the shallow part of the mantle over here. And with convection, we have a thermal gradient, dT/dP, that's equal to V alpha T over Cp. So this is the form of heat flow, or rather the temperature that's changed that's related to heat flow due to convection. Conduction is not part of the picture, again, because we think the flow is too rapid to allow the very slow process of heat flow by conduction to play any significant role.